Section 4.8, I titled it Rationalization, and the instructions are to rationalize the denominator. And when I say to rationalize the denominator, it just means to write a fraction that is equal to the original fraction, that doesn't have a radical in the denominator. You can't even freaking spell. Write an equal fraction. I'll say equivalent because it looks the same, but they're equal. So I'm going to write an equivalent fraction that doesn't have a radical in the denominator. And this isn't particularly hard, it's actually kind of easy. What I mean, this will be the idea of writing the equivalent fraction. Like if I had the fraction 1 over 2, if I multiplied the fraction by 3 over 3, this has nothing to do with radicals, but these two fractions, these are equivalent fractions. They both have a decimal expansion that's equal to 0.5. They look different, but their decimal is the same. That's more or less what we're going to do in this section. We're going to multiply by a fraction to take a fraction and change it to an equivalent fraction, fractions that are equal to each other. They look different, and they look different in problems 1 through 22. The difference that we want to make happen is we want the new fraction not to have a radical in the denominator. Super easy to do these. My calculator, such an awesome calculator. If I just entered problem 2 on my calculator and wrote 2 over the square root of 7, my calculator is actually programmed to rationalize the denominator, meaning it's programmed to write a fraction that's equal to this fraction that doesn't have a radical in the denominator. If I just type that fraction in and hit equals, that fraction, 2 square root of 7 over 7, its decimal would be the same as the decimal expansion of the original fraction, and it doesn't have a radical in the denominator. That's actually the answer to problem 2. To get to the answer, to create a fraction that is equal or equivalent to the original fraction that doesn't have a radical in the denominator, it's simple. I just multiply the numerator and the denominator by the copy of the denominator. For this one, if I multiply the numerator, it's out. I can't multiply a number outside a radical by a number under a radical. And in the denominator, both the numbers are under the radical, so to multiply the denominator, I multiply the 7s. This fraction and this fraction are equivalent because what I've multiplied by is a fraction that's equivalent to 1, and multiplying by some version of 1 changes the appearance of the fraction, doesn't change what it equals to. Now in the denominator, the square root of 49, I know that in my head to be 7. And that's what my calculator gave me. My calculator knows that this fraction can't reduce. I can't reduce the 7 under a square root with the 7 in the denominator that's not under a square root, because a square root is really a fraction exponent, and if you divided these 7s, you'd be doing division before exponents. So that's all there's to do for problem 2. For problem 1, I would just multiply the numerator and the denominator by the square root of 5 over the square root of 5. In the numerator, I'd leave the 3 and the 5 next to each other. You can't multiply a number under a square root by a number outside a square root. And in the denominator, if I'm not lazy, I'd multiply the 5's together. They're both under the radical and get a square root of 25. And then I'd reduce the square root of 25 to be 5. Usually, I get lazy. When I'm doing these rationalizing the denominators, anytime you multiply two identical square roots, you could bypass the showing what the intermediate step, anytime you multiply two identical square roots, it will simplify ultimately to what's under one of the square roots without the square root symbol. Usually I do that in this section. I speed up my multiplication. But if I wanted to, problem 1, 3 over the square root of 5, my calculator knows that that rationalizes to 3 square root of 5 over 5. I'll do problem 4. You might give 3 a try. To do 4, I'm going to multiply by square root of 10 over the square root of 10. In the numerator, I can't multiply a number outside a radical by a number under a radical, so I leave them next to each other. And in the denominator, technically I should do this. Multiply the 10s and get the square root of 100, but the square root of 100 is just 10. It would have been better if I skipped this step and said this is 5 square root of 10 over 10. And unlike problems 1 and 2, this is a reducible fraction. There isn't any adding or subtracting in the numerator or the denominator, and the numbers that aren't under the radicals are reducible. I'm going to reduce these. I'm going to reduce the 5 by 5 to a 1, the 10 by 5 to a 2. I'm not going to write the 1 in the numerator, but I need the 2 in the denominator. I'm going to say number 4 is square root of 10 over 2. Since it's a square root, I can check 4 on my calculator, do 5 over square root of 10, and my calculator should tell me that that equals the square root of 10 over 2. 6 is going to be harder, but anytime I'm asked to rationalize the square root that doesn't have any adding or subtracting anywhere in the numerator or the denominator, I can multiply the numerator and the denominator just by a copy of the denominator. In the numerator for problem 6, I can't multiply a number under a square root by a number outside a square root, so I just leave them next to each other, the 5 and the square root of 10x. And in the denominator, I'm going to speed lazy multiply. Anytime you're multiplying two identical square roots, like I did here, like I did here, like I did here, it will ultimately simplify to what's under one of the square roots without the square root symbol. I can't do this on my calculator, but I can still simplify it by hand. The radical part can't reduce. I can only reduce by dividing if the numerator and the denominator both had a radical, but I'd still, because it's straight multiplication, can reduce the 5 and the 10 just like I did in the problem above it. The 5 is going to reduce to 1, and I don't need to write that 1. And in the denominator, the 10 is going to reduce to 2, and I leave the x in the denominator. I can't simplify anymore. That's my answer for number 6. I can't reduce a number outside a radical with a number under a radical. I'll do 7 with you as opposed to 8, just in case these things aren't so readable. 3 is 4 over the square root of 6. 2 is 2 over the square root of 3x. And 6 is 6 over the square root of 3b. Or 7 is 6 over the square root of 3b, idiot. That's a b, not a 6. So I'm going to multiply numerator and the denominator by the square root of 3b. Square root of 3b. In the numerator, you can't multiply a number outside a square root by a number under a square root, so I just leave the 6 in front of the square root of 3b. In the denominator, anytime I'm multiplying two identical square roots, I get what's under one of the square roots without the square root symbol. And just like in my last couple problems, these numbers outside the radicals can cancel. I'll do 6 divided by 3 is 2, 3 divided by 3 is 1. For my answer to number 7, in the numerator I have the 2 that's left over when I cancel, the rad 3b that can't cancel with anything else, and in the denominator just the lonely b. And that b can't cancel with the 3b. I can't cancel something outside a radical by something under a radical. For what it's worth, it just seems blurry here. 9 is a over square root of a, and 10 is 2b over the square root of 2b. To do 10, I'll multiply square root of 2b over square root of 2b. In the numerator, I can't multiply something outside a radical by something under a radical, so I leave them written next to each other. And in the denominator, when I multiply two identical square roots, I get what's under the square root without the square root. And in problem 10, these two b's will cancel. Makes it so I cancel the entire denominator. I don't get a fraction anymore. And I just have the numerator that didn't cancel, the rad 2b left. Up through 9, or up through 10, none of the radicals that were given were reducible radicals. None of the radicals, if I did prime factor trees, were going to have any pairs. 11, and for the next few problems, the radicals are going to reduce. 11, if it's not readable, is 4 over the square root of 2x cubed. And 12 is 8 over the square root of 6x cubed. I'm going to get rid of the rationalize first and then reduce the radical second. So in 12, I'm going to rationalize by multiplying a copy of the denominator over itself. My numerator I'm going to write as 8 times the square root of 6x cubed. The denominator, I'm multiplying two identical radicals, so I get what's under one of the radicals. I could right now reduce this 8 with this 6 by 2. 8 divided by 2 is 4. 6 divided by 2 is 3. If I stop there, my answer isn't completely reduced because that radical 6x cubed, it's a reducible radical. The 6 part of that radical isn't reducible because 6 doesn't have any pairs in its prime factoring. But in the numerator, the x cubed part of the radical can reduce to an x in front of the radical and an x outside the radical. So if I reduce that numerator and bring an x in front of the radical, leave the 6 under the radical and an x under the radical, I get a fraction that's reducible because now I have an x in front of the radical in the numerator and 3x's in the denominator, and I can cancel. I snuck it in. Here I wrote the x cubed as x times x times x just to make the canceling easier. The x that I bring out front from simplifying the radical in the numerator will cancel with one of the 3x's from the x cubed in the denominator, leave me with 2 x's in the denominator. In terms of 12, my answer should be 4 square root of 6x over 3x squared. That can't reduce any more because I can't reduce something outside a radical with something under a radical. Let's do 13 together. So 13 is 3 over the square root of a to the 7th. Maybe pause the video and give it a go if you want. I'm going to multiply numerator and the denominator by the square root of a to the 7th. In the numerator, I'm just going to leave everything all jumbled together. I can't multiply something under a radical by something outside a radical. And in the denominator, I have two identical radicals, so that will simplify to what's under one of the radicals without the radical. The square root of a to the 7th in the numerator is a reducible square root. So I'm going to reduce that square root. And that square root of a to the 7th, when I do my prime factor trees, I get 3 groups of 2. So I'm going to get 3 a's out in front of my radical and the single a left over under my radical. The fraction's now reducible. In the numerator, I have 3 a's from the a cubed outside the radical. And in the denominator, I have 7 a's from the a to the 7th. If I cancel the 3 a's from the numerator with 3 of the 7 a's in the denominator, I'm left with 4 a's in the denominator. So for my answer, the a cubed in the numerator cancels completely. The a under the radical remains. And in the denominator, I'm going to get an a to the 4th. I could have just subtracted the exponent, 7 minus 3, to get that a to the 4th rather than doing everything that I did. So up through 14, we're dealing with square roots, and reducing square roots or rationalizing the denominators for square roots is easy. In 16, if I'm dealing with cube roots, If I just multiply two identical cube roots, like if I multiply the cube root of 2 times the cube root of 2, if I multiply two identical cube roots, I don't get something that's very nice. When I'm dealing with cube roots and I'm asked to rationalize the denominator, I actually need a 3 of a kind. Multiplying two identical square roots, you get an answer that's without a square root equal to one of the what's under the square root. But with cube roots, it doesn't work. Multiplying two cube roots gives you something ugly, but multiplying three cube roots gives you what's under one of the cube roots without the cube root symbol. So in 15 and 16, 17, 18, and 19, when I'm asked to rationalize a denominator that has a cube root, just adding one extra copy of the denominator, that's only producing two identical radicals. In a square root, that's fine because the index is 2. But in a cube root, you need 3 of a kind. So if I was doing number 16, which I can't do on my calculator because my calculator makes cube roots into decimals, to rationalize the denominator, I need to tack on 2 copies of the denominator. Because if you multiply 3 identical cube roots, you get what's under one of the cube roots without the cube root symbol. So if I was doing problem 16, because it's a cube root, multiplying by one copy of the denominator isn't enough. Multiplying by one copy of the denominator creates 2 denominators, and in a square root, 2 is enough. In a cube root, you need 3 of a kind. Doing this properly, the numerator would be 3 times the cube root of 4, because I multiply the 2's under the radical. The denominator, I multiply the 2's under the radical and get cube root of 8. The cube root of 8 is 2. Anytime I multiply 3 identical cube roots, I get what's under one of the cube roots without the cube root symbol. So this is going to be 3 cube root of 4 over 2. This 2 and the 3 don't cancel, and I can't cancel the number outside a square root with a number under a square root. Let's do 17 together. 17 is 4 over the cube root of 4. I'm going to multiply to get 3 of a kind, because if I have 3 identical cube roots multiplied, they will always simplify to what's under one of the cube roots without the cube root symbol. So if you're working ahead, think of beauty. If I'm doing this showing more detail than I need to, the numerator, I'd multiply the 4's under the radical and get a cube root of 16. The denominator, it's just going to multiply out to be 4, but if I want 4 times 4 times 4 is 64. And in the denominator, cube root of 64 is just 4. So ultimately, multiplying by two identical cube roots of 4's makes the numerator 4 cube root of 16, and it makes the denominator just 4. Those 4's, because they're both outside the radical, can cancel. And when they cancel, I don't need to write a fraction anymore. I'm almost to the point where I could say I'm done, but I'm not technically done because the cube root of 16 is a reducible cube root. In problem 16, the cube root of 4, because 4 doesn't have any 3 of a kinds in its prime factoring, I stopped. But the prime factoring for 16 is 2 times 2 times 2 times 2. If I stopped and said the answer is the cube root of 16, then I'm leaving a radical that's reducible because there's a 3 of a kind in the prime factoring for 16. So a better final answer for 17 would have a 2 in front of my radical and a 2 under my radical. That would be the best answer for 17. Let's skip the x's. I don't do cube roots on the test. You can try 19 if you want. Let's do a 4th root. In a 4th root, like in problem 22, 3 over the 4th root of 3, you need 4 identical 4th roots being multiplied for it to simplify perfectly. So to do a 4th root, I have to tack on 3 more copies of the denominator, because if you multiply 4 identical 4th roots, it will reduce to what's under one of the 4th roots without the 4th root symbol. So for my multiplication here, I'm producing a 4 of a kind in a 4th root. In the numerator, the 3 that's in the initial numerator just kind of hangs out, and the 3 3's under the radicals get multiplied and become a 27. In the denominator, all 4 3's get multiplied, and 4 3's multiply out to be 81. And I could have been lazy because the 4th root of 81 is just 3. In the denominator, anytime I multiply 4 identical 4th roots, it's going to simplify to what's under one of the 4th roots without the 4th root symbol. So I could have speed multiplied the denominator. The 3's are going to cancel. The 3 in the numerator that was in front of the radical will cancel with the 3 in the denominator that the radical reduced to. And the cube root of 4th root of 27 doesn't reduce because in a 4th root you need 4 of a kind, and I don't have 4 of a kind. So for 22, that's just going to be my answer. For what it's worth, if it's not readable, problem 21 is 1 over the 4th root of 2. So I'm going to do a part 2, and it'll be a short part 2 because I'm going to trim some of the problems because they're not quite as important. It'll be hopefully like a 10-minute short one. So pause it, and I'll do part 2 here in a second.